Hello, my student. This clip is the demonstration how to solve the problem in conjugate beam method. We are going to determine the slope and the deflection of the beam, and we are considering this overhanging steel beam. This beam has constant fractional stiffness. Do you know this? Fractional stiffness. Fractional stiffness is the E times I. E is the modulus of elasticity of the material, and the I is the moment of inertia of the cross section of the beam. Okay, and this beam is overhanging beam is subjected to 8 kilonewton at D and 4 kilonewton at C. They asked us to use the conjugate beam to determine the slope at A, slope at C, and slope at D. That is 3 points, A, C, and D. And also determine the deflection at C and D. Why don't they ask us to determine the deflection at A? The deflection at A is 0. Okay, it's the pin. So you don't need to determine the deflection as A. The phi sub A equal to 0. And they says the E is 200 gigapascal. So that's for the steel. And the I is 710 power 6 millimeter power 4. And if you may convert, the I may be 7 times 10 minus 6 meter power 4. And then finally, they asked us to draw the elastic curve of the beam properly. Anyway, we should start by drawing the elastic curve. Okay. What we have, the beam is pushing at the middle. See, if you have the beam like this, and if you put it at the middle, it's going to up like this. And then you have the 4 kilonewton on the other sides. So the shape of the beam should be like you see here. It's up to the magnitude of 4. If it's more, it's going to downward. If it's less compared to 8 kilonewton, that's n going to be upward. Okay, so that is going to be the shape of this beam. It's going to be something like this, and then there is something like this. If I can show you here, okay. So now the deflection supposed to have something downward here, and this one going to be for sure. This one going to be up like this, okay, and it won't go upward like this as I show you because that is 4 kilonewton. So the 4 kilonewton gonna take this one down here if it's small compared to the 8 kilonewton, or it can be like this if it's large compared to the 8 kilonewton. So we don't know it yet until we calculate it. Okay, and what I'm going to show you is this is going to be the zeta sub A. Okay, and what is going to be, this is going to be the, let me assume it first, this is going to be zeta sub D. Okay, and if we select our beam to change, okay, the concave upward to concave upward over here, this is going to be the inflection point. Okay, or you may call it IP. Okay, and then the curve, let's say, is going to change. It's up to you, but we don't know it yet. But it's going to be go down like this. If it go down like this, what we have over here is going to be the deflection at D. That is, with C. That is V sub C. And this one is going to be the V sub D. And also, if you like, this is going to be the slope. Okay, this is going to be zeta sub C. So that's going to ask us theta A, theta C, and theta D. So you may have to highlight this. Okay, this one, and this one. And they also ask us to determine this one and this one. Okay, this is now elastic curve is good to make you clearer how to solve the problem. And if you see like this, it's going to clear to you that you will determine what you like to have. So what the step? What the analysis procedure? We're going to what? We're going to draw the shear diagram. We're going to draw the moment diagram. Before we can draw the diagrams, we got to write the reactions at A and B. Okay, and after you got the moment diagram, you can convert it into the elastic weight. And also finally, you can draw the conjugate beam later. So the first point, find the reaction, okay, and draw shear diagram, draw moment diagram, convert it to elastic weight, draw the conjugate beam, analyze the conjugate beam. The shear is going to be the slope, and the moment on the conjugate beam going to be the deflection. Okay, let's start by first. Okay, we will analyze the beam for the reaction, and then to find the reaction, let's put this one is x sub y and x and y reference, and we have this one for 6.5. So our beam is gonna be like 6.5. That is going to be 9 meters long, and then if you like, you may just put it 6. Okay, that is 2, 2, and 2. That's going to make it a little bit more appropriate. So we have 2 meters. Sorry, 2 centimeters for 3 meters, and then we have the A is going to be the pin. So under the force, what we have is this one is 8 kilonewton. This one is 4 kilonewton. And then we're going to have the reaction here, the A sub y, and here of A sub x. And over here we have the B sub y, and we have all the length as shown here for 3 meter, 3 meter, and 3 meter. That's going to be the free body diagram of the beam. So first one, we find the reaction. Okay, and by using the scale of 2 centimeter per 3 meter. And then what you may have? You may have first one, very simple, summation of x sub x equal to 0. And then you get A sub x equal to 0. And then you may take the summation of moment about A equal to 0. Just take moment over here. So the B sub y. Checking about unknown. Unknown going to rotate upward. So this is going to be plus. And we going to have the B sub y. B sub y going to time what? B sub y going to time this length. That is going to be 6 meters. And it's going to be equal to 8. Okay, equal to 8. 8 times what? 8 times 3. Okay, it's in opposite direction. B sub y is up. This is down. This one also down. That is going to be plus 4. 4 going to time what? 4 going to time 9. Okay, time 9. So you got this one for 24. You got this one for 36. Okay, that is going to be 60. So your B sub y going to be 60 divided by 6. that is going to be 10 kilonewton. So your first B sub y here is 10 kilonewton. And then if you may have the what summation of F sub y equal to 0. And this one you're looking for the A sub y upward is positive. So your A sub y up. This one plus 10. Okay. And this one is downward equal to 8 plus 4. And then you may get A sub y equal to 12 minus 10. Okay, that's 12 minus 10. That's it's going to be 2 kilonewton. Okay, now you get the reaction. Okay, and after you get the reaction, the next step, we will draw the shear diagram and M diagram. Okay, next, if you like to draw it, you got to do some kind of projection of this beam. A very important point, A, B, C, D, E along the way from there to there, and you must put what you have here, the reaction, into the problem, because when we draw the shear diagram, we gonna take a look at the problem. So what we have, the B sub x is 2 kilonewton. So this one is 2 kilonewton, and this one is 10 kilonewton. And to draw the shear diagram, we just start by moving from the left to the right. Okay, by doing this, you have 2 kilonewton here. So the 2 kilonewton, let me zoom it up a little bit. Okay, 2 kilonewton gonna going up, right? Let me take 2 kilonewton for half centimeter. Okay, let's say we have 4 kilonewton for 1 centimeter, if you like, and then you put this as the V kilonewton. Okay, and this is going to be X meter, and then you get this for 0, you get this for 3, you get this for 6, and you get this for 9. When you get 2 kilonewton, your diagram going to be up for 2 kilonewton, and then when you come here, there is no distributed load, so the dV by dx equal to 0, and you guys gonna get this for a constant. Okay, and now you get this for 8 kilonewton, so it's going to take 8 kilonewton 2 centimeter, so it's going to be down 1, 2, about here. Okay, it's going to be down here, and what is going to be what? It's going to be plus 2 minus 8. That is going to be 6 kilonewton. That's going to be 6 kilonewton with the downward. Okay, a bit about this, and then it's going to be dV by dx equal to 0. This is going to be plus 2 minus 8. It's going to be, minus 6 kilonewton. This one also minus 6 kilonewton. Okay, and now it's going to take up of 10. Okay, that's up to 10. 10 is about this 2, 4, 6, 8, and 10. It's going to take up for 10. And that's it's going to be what? It's going to be minus 6 plus 10. That is going to be 4 kilonewton. And then over here has no forces. You can take this one. Okay, and you have this one for dV by dx equal to 0. Up until here, it's just close. That is going to be your V diagram. And next is going to be your moment diagram. That is kilonewton meter. Okay, and then you have this is the A, and the A has what? The A has no no moment. Since it has no external moment, that's one gonna be just be 0. And also at the C, you may see here, C also has no moment. Okay, that is going to be 0 kilonewton meter. Okay, this is going to be X meter. This is 0, 3, 6, and 9. And we start here with 0 kilonewton meter. And what? You know the moment diagram, you just need to take a look at the shear diagram. When the external moment is 0, you start with 0. And then when you come in, we have the shear of 2 kilonewton. So the slope over here, the m by dx is going to be equal to v, equal to 2. Okay, and what the moment here? We don't know it yet. The moment here is m. Moment here is m. Minus m over here is m sub d. Minus here, minus 0. And it's going to equal to moment here minus here is going to the area here. The area here is going to be 2 kilonewton times 3. So it's going to be 2 times 3. And then you're going to get m sub d of 6 kilonewton meter. Okay, that is going to be the value of moment over here. And you may say, okay, this is 6, right? Let's take this one as a centimeter. Okay, and your diagram going to be like this. Okay, and the slope here is here, and the slope here also is here. So that's the first part of the moment diagram. And then what? And then the slope change. This is dm by dx equal to positive 2. This one is dm by dx equal to minus 6. So the second portion we have the dm by dx equal to minus 6. That means your value of the moment gonna get lower and lower until you arrive at b. So what you have is m sub b. B is here. Okay, minus m sub d. Okay, minus here is minus 6. Okay, and it's equal to minus 6 times 3 equal to minus 6 and then times 3. So your m sub b gonna be what? M sub b gonna be minus 18 and then plus 6. That is going to be minus 12 kilonewton meter. So m sub b gonna be minus 12. So this is 6 for this is 6. This is 12. Okay, and then your curve gonna be like this. This is going to be minus 12 kilonewton meter. And the last one going to be easy because this is 0. So you can draw the line. But you got to say what the slope is. The slope here is here. The dm by dx equal to plus 4. And then if you like, you can highlight it. This is going to be plus 4. Okay, and if you like, you may put this one. This is going to be plus 2. And also you may put this one, this one, this one. That's going to be minus 6. Okay, that's quite a beautiful one. And what we have is this is the point of 0 moment. Okay, this is going to be the point of 0 moment. This is 0 kilonewton meter. So what is this? This is going to be 6 divided by x. So by similar triangle, 6 divided by x, 6 divided by x is slope is 6. So we have what? X equal to 1 meter. So this one gonna be equal to 2 meter. Okay, that is going to be your moment diagram. That is going to be finished this one. And if you may recall, what we do this, we have about 6 law, and I like to say it again. First, dv by dx equal to minus w. You may recall this. When you push over here, you get 2 kilonewton also. So that is going to be the third. When you got the positive, upward p, you get the delta v as positive. When you get the downward p, this is p, you get the delta p as negative. Okay, and then dv by dx, the slope equal to w. No, w slope is 0. Okay, and then you may have also this one, the delta v equal to minus area under w between a b, let's say, is in the length of AB. Okay, and also when you draw the moment diagram and you arrive at this one is no moment. Actually, you have the third condition of this. If the moment is like this, delta m is negative. Okay, and if the moment is like this, delta m is going to be positive. And then when you arrive here, since it's 0, so there is no change. And then the first one, you come over here, you have what? You have the shear, and then you have a shear of 2, so dm by dx equal to 2. dm by dx equal to v. And then you got to find what? You got to find m sub d over here, m sub d minus m sub d minus m sub a minus m sub a. So we have it equal to the area of V diagram. The area of V diagram. Under what? The area under V diagram. Under what? Under between the point. Not under what? Under between area. Between what? Between D and A. Between D and A. Okay, that's the review of drawing the shear diagram of the moment diagram. And now we are moving to the next step. We're going to do what? We're going to draw the conjugate beam. Okay, to draw the conjugate beam, again, you got to change the weight change the moment into the elastic weight, and change the support of the real beam into one of the conjugate beam. So let me take this part, second part, 1, 2, and 3. Draw the conjugate beam. Okay, I'm just going to think back and elastic wedge. Okay, the elastic wedge is kind of you may see that just change the moment, okay, and divided by the EI. That's just for elastic wedge. But for the conjugate beam, let us review. We need to change the condition of the beam, like we have to change for the free of the real beam to the one that's fixed. Okay, if you have fixed for the real beam you got to change it to the free end. Okay, and you also have, if you have the internal roller, okay, you're gonna change it to internal hinge. Okay, and at the same time, if you have internal hinge, you got to change it to internal roller. But for the external pin or external, let's see, external roller, is you have something like this, external pin or external roller. When you change it, it's going to be the same thing. Okay, it's going to still the same external pin and external roller. Okay, let's say this one of the left is going to be the real beam, and this one for the conjugate beam. Okay, this one, let's say, just put this one. This is the real beam, and this is for the conjugate beam, and this also the real beam, E-A-L, real beam, and this is going to be conjugate beam. Okay, that is going to be the guideline, so you can draw this. What we have is this is what? This is the fix, right? So you got to convert it into the fee, convert it into fix. So this one gonna be fix, and you convert the C to C palm. This one is what? The first one is fix, fee to fix, the fee to fix. The second one, what? We have internal what? Internal support, right? Right? And then we got to change it to hinge. So we change this. This one gonna be B palm. And the last one, we have external pin, and this one gonna be stay as the external pin. So beware about this. This is going to be the external pin. Okay, that is the conjugate beam, and this is going to be the A palm, and this is going to be the D palm. And now we're going to make the moment to be what? To be the elastic weight. To make the moment to be the elastic weight, we gonna what? We're gonna do some copy. So this one, if you like, you may put this one for 6. Going to be 6 kilonewton meter, 6 over EI. Okay, and this is going to be the first part of this. Okay, and it's going to move the elastic weight. The elastic weight here is always okay. If it's in the positive, it's going to be up like this. Okay. If it's going to be negative, it's going to be downward like this. So should be aware about this also. So this one going to be okay. And then this one is 12 minus 12. Just put this here, and then you have this 4, and this is going to be up. Okay, this is 6 kilonewton. This is going to be 12 over EI. No negative sign, because it's going to represent by this arrow and this arrow. Okay. And the last one is here. You may put this one. Okay, it's going to be downward because it's negative. Okay, that is the conjugate beam that you're supposed to have. And now we need to analyze the conjugate beam. So next step, the fourth one, we analyze the conjugate beam. When you analyze the conjugate beam, there is two theorems that we mentioned before. The first one, what? The zeta on real beam is what? Is V prime on conjugate beam. Okay. And the second we have the deflection on real beam is M prime on conjugate beam. That is the basis. You should know about this. And what happened is this is fixed. Okay, this is pin. We gonna divide this beam into two portions. One is AB, another one is A prime, B prime, another one is B prime, C prime. So let us separate the beam into two parts. The first part is going to be this portion, 1, 2, 3, 4. And this portion is going to be, let's see, 2 centimeter is 3 meter. Okay, so we have the same scale as before. The scale gonna help us. And what we're going to have is the reaction. And this one gonna be here. Okay, this is 6. Okay, this is 6 over EI. Then we have this. And also we have this one for the 12. So I'll take this one. This one is going to be like this. This one is, this one is 1 meter. This is 2 meter. And this one is downward. And due to this one is what? 12 over EI, right? This one is 12 over EI. And under this is going to be, this one is downward. This one is upward like this. And the other here is going to be also the same. This is going to be okay, let's we have this. So this is going to be 12 divided by EI. What we have is the reaction here is the A sub y prime, no A sub x prime, because the elastic weight is only in the vertical direction. And let we have here is here, this one up, this one down. This is going to be B sub y prime. And we also going to have here, let's say this is going to be V sub C prime. And we have the M, okay, the M here, the M here. This is going to follow the sign convention that we have. This is going to be M sub C prime. This follow the sign convention that we have. Okay, and this is 3 meter, and this is 3 meter. What we have, all the forces that we have are distributed load. So we got to determine the resultant force of this load. Let me have this one first. Okay, this one going to be what? This one going to be 1/2 of what? Of 3 and time 6 over EI, 6 over EI. So this one going to be 9 over EI. Okay, and then if you like, this one can be find the position of this. This is going to be 2 meter. This is going to be 1 meter. This is 1/3 of 3. This is 2/3 of 3. Okay, and the second one, we supposed to have this one, and again this position will be find easily. This one gonna be 2/3 of 1 meter. Okay, and this one gonna be 1/3 like this. Okay, let me zoom this so we can work on this easier. Okay, and then what? We have another one here. It's going to be the downward. This one must be the downward. And it's going to be what? Oh, going to be 1/2 over this one and time 2. It's going to be 12, right? 12. It's over EI. This is going to be 12 over EI. And the length of this, okay, is going to be what? This is 2 meter, right? So this is going to be 1/3 of 2 meter. And over here, this is going to be 2/3 of 2. That is going to be 4 over 3 meter. Okay, let me do a little bit highlight on this. This is going to be 9 over EI. This is for this area. Okay, you make something kind of a little bit clearer. This is going to be what? Did we determine this one yet? No, we didn't determine this one yet. We just take this one off here. It's going to be 1/2 of 1 divided by, time by 6 divided by EI. And this one going to be 3 over EI. So this one going to be 3 over EI. Okay, this is going to be 3 over EI. And we have another portion here. Okay, this is going to be 12. And we also has another one here, the last one. And what we have is going to have the resultant. That is going to be downward. Again, it's going to be 1/2 of this one time 3. 1/2 of this one time 3 is going to be what? 6. This 12 by 2 is 6. 6 times 3 is going to be 18 over EI. Okay, now you are going to be a little bit clearer if we try to show this, and distance here can be what? 3 meter, and this is 1 meter. So this is the free body diagram of this beam, and now we are ready to determine the reaction of this one. And before we going further to this, let us understand something. The a sub y prime here is gonna be zeta sub a. Okay, as we mentioned before, this is going to be zeta sub a. And m sub d here is going to be v sub c. M sub c prime. M sub c prime is going to be the deflection at c. And what is going to be v sub c prime here? V sub c prime here is going to be the zeta sub c. So if we determine the reaction here, at least we get some that we require to determine it. And what free body diagram should we start with? Which one? Which one should we start with? We start with this one or this one. And if you consider the free body diagram, you can see that this free body diagram have only 2 unknown, and this free body diagram have 3 unknown. And then it's better for us to determine the b sub y prime and a sub y prime first. And when we know b sub y prime, we put it here, we can determine the shear and the moment later. Okay. If you based on this concept, let me start by summation of moment. Let's say at here is better as a sub y, a prime equal to 0. Just take moment m sub a prime equal to 0. And what we have is b sub y prime gonna be what? B sub y prime gonna rotate this way. Okay, and we have b sub y prime. You take moment here. The distance from here to here is going to be 6 meters. So it's time 6. And you're going to have a lot of things. So this is going to be upward. And this one going to be the same direction. This one going to be in the same direction. So it's going to be plus 9 over EI. 9 over EI is here. Okay, it's gonna time the distance of 2 meters time 2. Okay, and you also have this one is 3 over EI. And then you time it by what? This is going to be 3 meters, and this is going to be 1/3. Okay, and now it's going to be equal to what? This is going to be counterclockwise. This is clockwise, so it's going to be equal to 12 over EI. And this, how far away from here? You may see that this is going to be what? 6 meters, and this is going to be 2 over 3 meters. So you're going to time this one going to be what? If you like, you may put this one 3, 4, and plus 4 over 3. Okay, it's going to be the same thing as 6 minus 2/3. It's up to you. You may put this 6 minus 2/3. Okay, it's going to be the same thing. And then what you're going to have is what? From this, just put it into your calculator. You got to have like 6b sub y prime equal to, if you move all around here, 36 over EI, 36 over EI, and then you may have b sub y prime equal to 6 over EI. Okay, and this is going to be the, if you know, this is going to be the zeta sub b. But the problem didn't ask us to determine this, but it's okay. We need to determine it because we got to have this one to determine this two. So this is going to be 6 over EI. And now you get to find the zeta sub A. If you like to determine the zeta sub A, it's better to put the summation of f sub y equal to 0. And this time is downward. So it's downward, is positive. Okay. And you have this one for A sub y prime. A sub y prime downward. And this one plus 12 over EI downward. And this one is upward. Minus 6 over EI. And this one is upward. Minus 3 over EI. Okay. And this one minus 9 over EI. And that is going to be equal to 0. And you may see this one and this one, cut this one. So you will have A sub y prime equal to this one, 6 over EI. 6 over EI. And you also know this one, this is going to be the equal to zeta sub A. Okay, and also if you find this one already, you're going to go back to determine this. Okay, this is the first part of our calculation of this. And if you like to go further, let us, it's okay, just take from here. I got to zoom it out a little bit. So I have the area to do the calculation. Okay, let me have this area to create it up. Okay, and let's make this one. What we have is now we have this already of 6 over EI, and this one 6 over EI. Then we will determine phi the V prime sub c, which is equal to zeta sub c, and M prime sub c, which is equal to V sub c. Okay, we just start by doing this. Okay, and what we have is you can use any equation to find this. Let me use the summation of f sub y equal to 0. And we have what? We have the downward is positive. So we have the V sub c prime. So we have V sub c prime is downward, right? And this one downward also plus 18 over EI is downward. And also this is downwards plus 6 over EI and then equal to 0. So we have what? We have V sub c prime equal to zeta sub c, and then equal to this one is going to be minus 24 over EI. Okay, that is the shear. And then if you determine the moment, you got to summation of moment at c prime equal to 0. And this time your moment is rotated like this. So put the counterclockwise is the positive. And then you have m sub c prime here. So the m sub c prime allow here. And this one also going the same direction. And this one also going the same direction. This one gonna time 2. So we have plus 18 over EI, and then it's gonna time the distance here is gonna time 2, and then this is gonna be the same direction. It's gonna be plus 6 over EI. Okay, and this is gonna time 3, and it is 0, equal to 0. So this time you may get m sub c prime, m sub c prime equal to v sub c. And if you do this, this is gonna be 18, this is 36. Okay, that is going to be equal to minus 54 over EI. Okay, you have 2 more. This time you got zeta sub c, and you also have the v sub c. And if you recall, we have the E of 200 gigapascal. So if you like, you may put to this as equal to minus 54 divided by. We calculate this by using kilonewton. Okay, so the E gonna be 210 power 6. This is going to be Newton per meter square, from 10 power 9 to 10 power 6, because this is kilonewton. And the I, if you recall, this is going to be 10 minus 6 meter power 4, if you may recall that. And then if you put this into your calculator, this one gonna cut. Okay, and you going to have this for it's in millimeter, right? And 38.6, it's going to be 38.6 10 minus 3 meter, or you may get this one for 38.6 millimeter downward. Okay, you may have this already at the answer. And again, if you do for this one gonna be what? This one gonna be minus 24, and then divided by 200 and times 7. Number when you same, this cut, this is 200, and then 7, and then you get this one of how much we get? Minus 0.0171, and it's going to be in radian. Okay, this is supposed to be double cross line, and then you get this. And you also, if you like to find the zeta A, okay, you may put this one again. The zeta A is going to be equal to divided by 6. Again, the divider gonna be 200 and times 7. So that is gonna be 4.29. This is 4.29, 10 minus 3 and radian. Okay, and if you're interested in this one will get the same result of this one, 2.49. Let's put this one in the and the direction of the zeta A, zeta C, we will determine later when we draw the elastic curve. Okay, and we still have one more to work on. Is the deflection and the slope at D. Okay, so let us move to this portion of the conjugate beam, and now we are going to take a look at the portion of this. If we find we find what? We find zeta sub d. That means we're going to find v sub c palm. And what? And we find v sub d. That means we're going to find m sub d palm. So by doing this, that means we got to draw the free body diagram of the portion A palm, D palm. Okay, and for this, what we have for the A palm is here. Okay, that means we have this one is downward, and it's going to be 6 over here. And also we have this force. This one also 6 over EI. And we have, okay. Okay, that is free body diagram. This is the A palm, this is the D palm. And at that section, what we have is this one, M sub D palm, by using the sign convention that we have. And this one is V sub D palm. Okay, now we are ready to determine what we are looking for. And if you like to start, we may start by summation of f sub y equal to 0. And if you determine this, and also if you may recall from here, the resultant force here is going to be 9 over EI. This is 9 over EI. And this is 2 meter. This is 1 meter. That is total of 3 meter. Okay. So V sub D palm is downward. So downward is positive. And we have V sub D palm downward. And then we're going to plus 6 over EI downward. And then you're going to have what? This is upward. Equal to or minus 9 over EI. And if you do so, we will have V sub D palm, in which is going to be equal to zeta sub D. And it's going to be equal to 3 over EI. Okay. And it's going to equal to what? It's going to equal to 3 divided by 200 times 7. Okay, and it's going to be the value of what? 0.00214 radian. Okay, that is going to be our next result of what? Of zeta sub D. Okay, this is zeta sub D. And the last one that we have is the M sub D palm. So we use the summation of moment M sub D palm equal to 0. And counterclockwise is positive. So we have this for. Okay, take moment here. And we have M sub D palm. Take here. What we have is 6 kilonewton gonna rotate in the same direction. So 6 kilonewton gonna times 3. And this is going to rotate in opposite direction. You may see it's very inconform to this one. This 9 over EI. And 9 over EI going to time only this. It's going to time 1. Okay. So your M sub D going to be, this is going to be 9. This is going to be 18. when you move it, your m sub d prime gonna be 9 over ei minus 18 over ei is gonna be minus, okay, 9 over ei, 9 over ei, or is equal to 9 over ei downward. And you know that this one gonna be v sub d, okay. And then if you push it into your calculator, that is gonna be divided by 200 and times 7, and then you got this for 0.00643 meter, and it's downward, okay, or is equal to 6.43 millimeter. That is going to be v sub d. Okay, that is going to be our last calculation, v sub d. Okay, now we put everything together. Okay, v sub d, deflection at d is going to be 6.43. This is 6.43 millimeter downward. Deflection at c, 38.6 millimeter, 38.6 millimeter downward. Slope at A, slope at A here is 4.29 10 minus 3, 4.29 10 minus 3 radian, and I'm very sure it's going to rotate this way. Slope at C, we have slope at C is here, it's going to be 17.1, 10 minus 3 radian. Okay, slope at C, and we check later how it's going to rotate. And slope at D is going to be here. Okay, it's going to be 2.14. It's going to be 2.14 and 10 minus 3 radian. Okay, from this calculation you can see that the NC, okay, gonna have very large deformation and slope. Okay, if you like to do this, and what is going to go downward. Okay, if we follow this, let's just me put this one here, and let this one have the about 40. Okay, and let's see, let's me put like a 40 millimeter deflection to be 1 centimeter. So this one gonna get downward to here. Okay, and this one gonna be here, no movement. This one gonna be here, no movement. And we have this one for 6.43. Okay, that's 6.43 is going to be very small. This is 4 millimeter by 1 millimeter. That is going to be very small here. The deflection here is going to be 6.43 millimeter. That is going to be V sub D. So this one V sub C equal to 38.6 millimeter. So and also if you come here, you also have inflection point 1 meter from that. So that is going to be about 7 millimeter over here. Okay, this is going to be inflection point, the location. This one is not correct. Okay, this one is correct. It's only 1 meter. So 1 meter is about this. Okay, and what we have is this one will be covered. like this. Okay, and this is going to be the zeta sub A, and what we have is going to be 4.29 10 minus 3 radian, and when it's come here, it's going to be let me zoom it a little bit, concave upward, and then the other going to be concave downward. Okay, this part is going to concave downward. Mix like this. That's it's going to be pretty big concave downward like this. Okay, that is going to be that, and what we have is this is going to be the V sub C, and what we have here is going to be, okay, this is going to be zeta sub C. It's going to be 17.1 10 minus 3 radius. That is big compared to this one. And the slope here going to be like this. Okay, it's going to be here of 2.14 and 10 minus 3 radian. Okay, that is going to be the elastic curve that's properly portioned and going to give you all the direction you may require to put into your answer. And you may can see that our first draft of elastic curve is not exactly right, especially at the D, which is really small. Okay, compared to V sub C here, it's more supposed to be larger. Okay, and if you like, you may put the direction of this zeta sub C gonna rotate like this one. Okay, and this one is going to rotate a little bit this way. Okay, that's all we have for the demonstration to solve this problem, and for sure you can have examination on the conjugate beam that we will let you solve for the slope and for the deflection. Okay, that is the end of these clips. Bye bye.